Today I'm going to talk about acceleration. So what is acceleration? Well, acceleration is quite close to the idea of velocity. So let's imagine there's a car or something driving and it starts at a point, 0, with 0 velocity. So t equals 0, 0 velocity. And it ends at some time, we'll just call it t2, with a velocity of 1 meters per second. So over the course of this range of t2, um, this velocity changed. And so not only did the position change with time, which is velocity, but the velocity also changed with time. And so acceleration is not how our position changes, but how our velocity changes with time. So you can think about it as a velocity of a velocity. So it's how fast your velocity changes over time. So if t2 is 1 second and your velocity goes from 0 to 1 in 1 second, then your acceleration is 1. If it changes to 2 meters per second, then your acceleration doubles. And so if you watched my previous videos on velocity, the equations will look quite similar to this. So our average acceleration, we can think of average acceleration just like average velocity, is our velocity at the point 2 minus velocity at point 1 divided by the time at point 2 and the time at point 1. So this is our average acceleration. I almost wrote velocity. Okay, and it's also a vector because velocity is a vector and displacement is a vector, so acceleration must also be a vector. Okay, let's do a quick example of average velocity. So if we have, again, I'll draw a line for an object moving from a point where t1 equals 0, v1 equals 0, and we move to a point t2 equals 10 seconds, and v2, velocity, equals 30 meters per second. So to solve for the acceleration, we just take our v2 minus 0 over 10 seconds minus 0 seconds. And our acceleration works out to 30 divided by 10, which is 30 meters per second squared. So note the units here of acceleration are meters per second squared, which is the same as meters per second per second. So it's like velocity per second. Okay, so that is quick introduction to average acceleration, and it's exactly the same logic, the same math as for average velocity. But with acceleration, we can also think of instantaneous acceleration, where you want to find the acceleration at a specific point in time. So if I draw a graph, and we have some curve, and this is all exactly the same as for velocity. You could have your average velocity between some 2 points here. Sorry, I keep saying velocity. Acceleration, average acceleration. But if you wanted to find the average acceleration at P3, then, you'd have your, here, let me draw this in red. You'd have your average with your delta t and delta x, where this is the t-axis and the x-axis. and you'd squeeze this delta t to 0 so that this width is 0. And I explained that in the video on instantaneous velocity, but what that looks like is v at p3 is equal to the limit as delta t goes to 0, which is just calculus terminology for what I just described. Sorry, this should be actually, I'm doing velocity here. This should be velocity axis, and this should be change in velocity. So that's the only difference between these two things, is that between acceleration and velocity, is that this is a v versus t graph, and in the velocity case, it's an x versus t graph. So we take the limit as delta t goes to 0 of delta v over delta t, which is the same as the derivative of velocity with respect to time. So if you go back, if you if you're having trouble understanding, I encourage you to go back to the video I did on instantaneous velocity, and the only difference in the equations is the v's change to x's. Now there's one more thing to think about with this, and we could take it a step further. And what I mean by this is that we remember that velocity is just the derivative of position with respect to time. But acceleration is derivative of velocity with respect to time. But this can be plugged in for this, so we get something like acceleration is the derivative of respect to time of the derivative of x with respect to time. So we've got the time derivative of the time derivative of x with respect, well, time derivative of x. And this is called a second derivative. So I can write it like this: d squared x over dt squared. So this is the second derivative with respect to x, or second derivative of x with respect to time. So in other words, if you have an equation for position, you can find the acceleration by differentiating it twice. So you take one derivative, and then you do a derivative of your derivative, and that would give you the equation for acceleration. So I'll write a nice equation out here where acceleration, let's see if you can see that, acceleration is equal to derivative of velocity with respect to time, which is equal to the second derivative of position with respect to time. And so that is an introduction to acceleration in both its average and instantaneous forms. Thank you for watching.